Want to learn about forces? Well, here's an introduction to forces. It's me, Moser. And after this video, you should be able to correctly identify the Newton as the SI unit for force, distinguish contact from field forces, and represent forces using a free body diagram. That's not so hard. So force is just an interaction between an object and its environment. It's what causes acceleration. You know what that is. And when we measure force, we use the SI unit, the Newton. So 1 Newton is equal to 1 kilogram times 1 meter per second squared. Okay. You probably remember from somewhere that force is equal to the mass of an object times the acceleration that the force creates on the object. Well, if we do a little bit of dimensional analysis, what that tells us is that 1 Newton of force is enough force to get a 1 kilogram object accelerating at 1 meter per second squared. Pretty cool. That'll come in handy later, but for now, if you just know that the Newton is the SI unit for force, we're good. When we think about how a force acts, there are 2 general broad categories: forces that act on contact and forces that can act at a distance. So contact forces we're all very familiar with. You know that if you push on something, it'll start to move, and contact forces result from actual physical contact between 2 objects. This ball has been contacted by this bat, and it's accelerating. This ball, though it's currently sitting still, is about to be contacted by this foot, and it's going to start to accelerate. And it looks as though these 2 brothers are in all sorts of contact with one another, and I suspect one of them is going to accelerate soon. The other category of force action are those forces that are capable of acting on objects when they're not touching. These are field forces, and gravity is the one that we know best. All objects that have mass have gravity, but the gravity that we're familiar with is that of our good old Earth. You're very attractive to the Earth. She just keeps pulling you back down. Gravity is a field force, and the Earth's gravitational field extends out to the edge of the atmosphere. Another field force that you're probably familiar with is that is generated by magnets. Earth has a magnetic field, and we've got lots of little magnetically charged objects around us every day. Go ahead, grab a magnet and some paper clips. Have fun. Now, force is a vector, which means, of course, that it has both a magnitude and a direction. And just like every other vector we've dealt with, from displacement and velocity to acceleration, oh boy, we can represent this graphically. So this is a vector representation of a force of 10.0 newtons to the east. Don't forget, for any vector, you have to have both magnitude and direction. So let's talk a little bit more about how we show force vectors. The 2 ways that we typically show force vectors are either through force diagrams or free body diagrams. Force diagrams show all the forces in a situation, all the objects, every force acting on each object. They get really messy really fast. Free body diagrams, on the other hand, which are the ones that we use much more often, show only the forces on one body in a situation. This is what we use far more often because they're really simplified. We very often simplify it even further and show objects as just sort of boxes or points. So to draw a free body diagram, first you draw the object in isolation. You can either do approximate shape. Cars very often look something like this. Or you can just do very simple boxes, squares, or points. but you try to position the object somewhat accurately. If something is tilted in a certain direction, you'll want to show it tilted. If it's on a ramp, you want to show that. Then you draw and label each force that's acting on the object. And forces are always shown acting out of the very center of the object. They get labels with the magnitude of the force and the name or origin of the force if we know it. Because they are vectors, it's really important that they have arrows on the ends. You'll remember that from our work with two-dimensional motion. And you want to make sure that all those forces are shown acting in the correct direction according to the problem. So let's practice one of these together. A box has 100 newtons of gravitational force acting down on it, a 100 Newton force acting upward from the table, and a cat is shoving it towards the edge of the table with a 10 Newton force directly to the right. Now, it might be all kinds of fun to draw adorable cats and funny little boxes and tables, but if we're going to do a free body diagram, we're going to simplify, simplify, simplify. Here's my box. That was simple. And I'm going to draw 100, I'll start with my first force. I'm going to draw 100 Newton force of gravity. It's acting down there. But, of course, I also have, and very often we color code our forces, I also have that 100 Newton force from the table that's acting in opposition to gravity. So we could call this the force of the table, and that's also 100 newtons. Note that I've tried to make those arrows as much the same size as possible. Because of the fact that these are both 100 Newton forces, the only difference we should see in them is the direction they're pointing. Now, the cat is shoving it towards the edge of the table with a 10 Newton force directly to the right. I've put my force of cat on the object, I've labeled it, and I've pointed it to the right. That's it. It's not really that hard. We use free body diagrams all the time. You'll pretty much never do a forces problem that you don't start off with a free body diagram. They're tremendously helpful when you want to analyze or resolve vectors. So, go practice! Section review in your Holt Physics book on page 128. This is the Chapter 4, Section 1 review. Numbers 1 through 6 are assigned. Take care. Have fun. Force it.